Okay, to continue with friction stir welding, here as I was talking about that, as you can see, if the temperature of a metal, I mean here obviously we are talking about steel, and it is true for other metal also. So, as the temperature increases, your stress level needed to yield the metal reduces, and that is basically is the logic or the practice which is done in case of what you call forging. If you have checked the if you have seen the operations of metal forging, what they do, they heat it up. Say a steel rod, you want to give it a shape, you heat it up to when it becomes bright red, then you just slowly hammer. The blacksmithy worker, he slowly hammers it and brings it to the required shape. What is basically happening there? Because of the increase in the temperature, the stress level needed to deform it is much less, or in other words, the yield stress has reduced, right. So, same thing is happening here in friction stir welding. Through this friction stir welding tool, which is sort of producing, which is giving a friction between the tool and the plate, giving rise to a temperature rise, giving rise to a heat leading to a temperature rise. The metal below the tool is coming in a state which is in a plastified state. It is not liquid, but in a plastified state, which can sustain mechanical deformation, right, which can sustain mechanical deformation. So, that is how the name also you can see, friction stir welding. Through the friction you are generating heat and then stirring the material. The material is fluid enough to stir it. Anyway, here a cylindrical shoulder tool with a profile pin is inserted into the joint line. We will see a schematic of that. Heat is generated primarily by friction between the rotating translating tool, rotating as well as obviously translating, because when you are doing the welding means you have the weld, this is the plate interface, right. There are the two plates. So, you have the tool here which is rotating, right, as well as moving forward. So, in the process what is happening? It is turning the material, that pin which is plunged inside is turning the material continuously and going ahead. So, in the process as if it is throwing the metal from here to the other side and going ahead. So, heat is generated primarily by the friction between the rotating translating tool and the shoulder of which rubs against the workpiece. Plates are strongly clamped with a backing bar below the weld. So, if this has to be done, the plate needs to be clamped very strongly, because if they are not clamped, then it will try to separate each other, because what is happening, it is something equivalent to that of a drilling operation. If you have seen, you put the drill bit inside the material, there what happens, it cuts out the metal and throws off the metal. That is how that drill bit, you have the helical kind of those cutting edges are formed, such that when it rotates, it will cut the material and throw off the material at the top, right. But here there is no question of throwing off material, it is a blunt head which is going in under force, right. And there is a shoulder on the top which is also rubbing against the plate surface. So, obviously, you will have to have the plates clamped strongly such that they do not move apart, because the root gap has to be 0. Root gap 0 means two plates should remain in touch continuously, because if the root gap is there is some root gap, there is no question of filler metal here, so welding will not be proper, right. So this is what is the schematic expression of this. As you can see, this cylindrical member is the tool, which has a kind of a nib or a pin at the below, right. So this intersection of the pin and the cylinder is the shoulder. This white circular region is the shoulder of the thing, and this is how the welding is being done. That means there are the two pieces of plates with zero root gap, as you can see, right. With zero root gap, they are been placed together. Obviously, they are solidly clamped on both the sides such that they don't move out, and a downward force is applied on the tool, which is rotating, having a suitable amount of torque, right, and it is the transverse force is provided because it should move ahead. The tool should be rotating as well as going ahead. So while it is rotating, and you will have to provide a downward force such that the proper friction takes place, and as well as the pin can plunge through. That pin will have a sufficient blunt diameter. It's not like drill bit which cuts in and goes inside. So here you need much higher downward force to have it plunge through. But obviously, once the friction starts, then this stress becomes less, stress required. So you do not need truly, I mean, had there been no friction, you try to plunge, put the that nib plunge in the plate, you cannot in the cold metal, simply you won't be able to do. But once it's rotating, so it's giving friction, generating heat, plastifying the material, so you can put it inside, all right. And then you have to provide a forward motion to the tool. That means a transverse force is also needed, which will push through the metal, but obviously the metal is in a plastified state, so it can push through without much force. But still that force also should be, I mean, this nib, there the nib design depends, that the force, the nib, this area, etc., and the stress, I mean the strength of this material should be enough to withstand that force, otherwise the nib will break. So that is what it is schematically. So here what you see, the nib is forced into the plates at the joint until the shoulder contacts the plate surface. That means, as you can see, as we lower down the tool, the nib will first touch the plate surface. You further apply downward force, then the friction will start heating up the nib tip. The bottom of the nib, that tip will start rubbing against the plate, generating heat. Local plastification will take place. Apply further downward force, it will plunge through. The metal will become soft enough, plunge through. Till what point it will plunge? Till the shoulder comes and touches the surface. Right. And there, if you apply further force, what will happen? Then this tool will try to plunge into the material, because here you see these lines, here the metal has got heated up because of the friction. So the metal here is soft enough. If you apply further force, this will try to plunge inside and will expel the material from these sides. It will sort of cut through this, along these edges. So this, how much downward force you are applying, that becomes one of the important parameter. Like in fusion electric arc welding, the welding parameters were the welding current, the voltage, the speed of the nozzle, speed of the electrode, right. So here the welding parameters are this downward force, right, at what RPM it is rotating, the RPM, what is the transverse force, right, and well, these are the your so called welding parameters. And other parameters are like what material this tool is made up of, because if it is made up of a material having high thermal conductivity, it will have some performance. If it is made up of a lower thermal conductivity, again it will have some different performance, very different performance, for the simple reason, obviously logically this tool material should be of a material having much less thermal conductivity, otherwise lot of heat will be wasted, dissipated, right. So, that is one aspect. Other aspect, the frictional coefficient should be as high as possible, frictional coefficient of this material, right, rubbing against the steel surface should be as high as possible. At the same time, this material, the tool material should be of such, should have such mechanical property that it can sustain higher levels of temperature. Sustaining higher level of temperature means what? Means the strength of the material remains still high even if the temperature is raised. Like here we can see the strength, what this curve means. This means the strength reduces as the temperature increases, right. So, this tool material should be such that there the reduction in strength should, obviously once the metal is heated up, there will be some reduction in strength, but even after reduction it will have sufficient strength to withstand this force, transverse force, this traveling, because it will be pushing through, right. Anyway, so the process is a downward forging pressure from the shoulder helps to prevent the expulsion of softened material. When you are pushing it through this nib or the profiled pin, so this is displacing the material. So, where the material is going, it will try to, when you put it in, it will try to get expelled, come out. So, that is what it says, that this shoulder prevents that from happening, coming out, but you should provide a space for it. So, what is done is this shoulder is made little concave inside, such that it can accommodate that expelled material, and also that provides a supplementary frictional heating. That means primary heating is from the nib, right, and then additional heating from the shoulder surface. It plasticizes a cylindrical metal column around the pin and immediate material under the shoulder. As the tool is moved forward, material is forced to flow from the leading edge to the trailing edge of the tool, leading edge to the trailing edge, from one side to the other, as we were saying. Well, if it is rotating like this, so from the leading edge to the trailing edge, it will go like this, right. The material that flows around the tool, that material movement is taking place. So, whatever material is flowing around the tool, it undergoes extreme level of plastic deformation, because till now by plastic deformation we knew that bending of a plate, elongation of a rod, right, but here it is a total dislocation of the material is taking place. The entire metal is getting, it's because the ultimate sort of plastic deformation is when the metal becomes liquid, it just flows, right, extreme displacement then, okay. But here it is just before the liquid state, it is not liquid, but so called soft enough, like for example you may have seen those putty kind of thing, plasticine, the kids they play, you can make any shape, right. It is not liquid, but it is fluid enough, soft enough to give it any shape, and it holds there, right. Similarly, the metal has become to that state of a plasticine. You can move the metal as you wish at that temperature, of course. The moment temperature is removed, it solidifies, it becomes hard, solid. So, that is the principle being used here. So, the material flows around, that is why the term flow is being used, though it is not liquid, it is not a liquid flow, but it is equivalent to that. So, the dynamics of this material movement can be modeled using the principles of fluid dynamics, right. So, the material that flows around the tool undergoes extreme level of plastic deformation. Significant benefit of this process. Why should we do this? What are the benefits? As I have mentioned in the beginning, that apart from, since here no melting is taking place, so all the defects related to melting are automatically eliminated. They are not there. Other additional advantages are, here we have very few variables that must be controlled. As I said, that in this the few basic operators, basic parameters are the downward force and the RPM. These are the two most important parameters. Tool rotation speed and obviously the travel speed and the pressure. Pressure is nothing but the downward force, how much you are applying, at what speed you want to move that, and what is the RPM. These are the three primary variables which needs to be controlled. Whereas, if we compare with fusion welding, again the primary variables were current, voltage, speed, and then you had electrode diameter, then you had root gap, then you had the length of stick out, right. Then you had the orientation of the electrode, you had polarity of electrode, all these were affecting the weld deposit. You change any one of them, the weld deposit will change. So, you will have to have a total control or a total sort of a optimum selection of all these around 8 parameters, and also there are shielding gas, what type of shielding medium you are using. So, all the 8 to 9 such parameters are to be controlled properly, such that you get the proper weld bead, proper joint quality. In comparison to that, here we have as such only these 3 are to be controlled, but here what we are assuming, that we are assuming these 3 for a given type of tool geometry. For a given type of tool geometry. Tool geometry means this tool, here it is schematically shown, a simple tool with a tapered pin. Here, as it has been shown in the diagram, it is a tapered cylindrical pin, but this tapered cylindrical pin can be of different types. It can have a helical shape, it can be trapezoidal kind of thing, not necessarily cylindrical, it can have threads in it, different types people have tried. So, for a given tool, there are the only 3 parameters which needs to be controlled. So, there is a unique combination of shear and normal. Well, so in FSW what basically happens, it is essentially a combination of a normal force and the shearing forces. They are the 2 kind of forces they act. So, here we are explicitly talking about what are the advantages. Here the high quality weld can be achieved. What is that high quality is? With the absence of solidification cracking. There is no question of cracking. If you want to see what solidification cracking means, you can come to the workshop in our lab, in our department. We have just done some welding where you can see a very nice solidification, I mean a case of solidification cracking. What has happened is a simple fillet joint was made, a T was welded like this, that with 2 members. This is called a T section, T configuration, and this welding is referred to as fillet welding. So, both sides welding was done. After it's still hot, right? That means welding has just over, and immediately you see a crack, through and through crack forming at the middle, all along the length, all along the length. So, that is what is referred to as hot crack. That means, while still the metal is hot, it is cracking, and also referred to as solidification cracking. Means it is getting solidified and the cracking is taking place. The metal is getting solidified, right. This is your deposition. This is the fillet deposition, right, and along the green line you find a crack developed all along. That is what is referred to as solidification cracking. So, if there is no melting, this possibility of such cracking will not be there. Anyway, similarly, no porosity, right. Porosity means it is caused by because of gas entrapment. No oxidation, because there is here there is no necessity of shielding, because the temperature rise is such that there is not much of oxidation is taking place additionally, right. So, requirement of shielding is also not there. Other defects resulting from traditional welding, fusion welding is also not there. Basically, all which are involved with fusion, they are eliminated. And another aspect here, what we see is apparently lower energy is needed, a lower energy input is there, the rate of heat input is less. So, leads to less distortion and residual stresses, because since the metal is not melting, means obviously I am putting in lesser amount of heat, When I am doing fusion welding, the amount of heat going in is more, but of course, this is not always true, because in fusion welding there can be situation where heat going in is more, but the rate at which it is going in is less. If I can increase, say, electron beam welding or say plasma arc welding or laser welding, where you have a very intense heat source, but because of the intense heat source I can instantaneously melt the necessary material which is being welded, I can instantaneously melt the required amount of electrode. So, I can as well have a higher speed of movement. So, the rate at which heat is going in is less. What is important is rate of heat input, not the absolute heat input, the rate of heat input. At what rate, that means how many joule per meter is being deposited. So, in FSW what happens, the overall absolute heat generated is less, but at the same time the speed of welding is very less here. In fusion welding one can achieve a higher, much higher speed of welding. So, even if the overall absolute heat is more, since the speed of welding is higher, so rate of heat input can be less, whereas in friction stir welding the absolute heat generated is less, but speed is also less. So, rate of heat input can be higher, but depending on cases it will have a lesser rate of heat input and thereby less distortion and residual stress. Well, now let us come to little more in detail about the tool geometry, because the tool is the heart of this process. In electric arc welding, it was essentially the electrical power, right. It was essentially the electrical power which worked towards the generation of heat, the fusion process, and thereby the welding. Now, here the most important aspect is the tool, the friction stir welding tool. So, optimum tool design will produce the desired joint quality as well as enable higher welding speed and longer tool life. So, these are the aspects. You not only you need a good weld quality, you need good speed as well as good tool life, because here like in welding we had the welding torch that has a very high life, the torch does not get damaged. The welding torch through which the electrode comes out, say in a gas metal arc welding, or the nozzle in case of a submerged arc welding, they have a very long life, they do not get damaged. electrode goes in, it melts, it gets deposited, but here the tool, it gets damaged. You have to replace the tool, possibly, I mean, depending on its life. So that is, so these all aspects, they depend on the geometry also. The shape of the bottom of the tool shoulder affects the material flow around the tool nib. How the bottom of the shoulder will be, right, that also will again depend. It can be flat or can be concave. That means this shoulder part, it can be flat, there is no harm, one can keep it flat, or it can be concave. So the small changes can cause a sufficient change in the entire operation, in the weld quality, in the entire operation speed. So as we say, it can be flat or concave, it can be smooth or grooved with concentric or spiral grooves, right. So a concave shoulder has an advantage, as I was saying, compared with a flat shoulder. That shoulder, so this is the nib, a small cross section of it. So this part is the shoulder of the nib, this part is the shoulder of the nib. So a concave one, this is a concave one, has an advantage. What is that? It directs material flow to the center close to the tool nib. Firstly, it has some space here, right. It has been concaved with an angle of alpha, some concaving has been done, right. So there is a small additional gap is there where the extra metal, when this nib is plunging into the plate, some material is getting displaced, so some metal will tend to come out. So when the metal is tending to come out, because at the back you have a backing strip, is holding the plate. That means in the welding, or maybe you have there is a backing strip there, a flat piece of plate is kept at the back, right. There is no need of, here the question of bottom top reinforcement doesn't arise. After welding, it will become one flat uniform plate. In all other fusion welding, we had a top reinforcement, we had a bottom reinforcement, right. Additional metal was deposited. Here it is not there, it will be flat both at the top as well as at the bottom. So once the tool is there, so once the tool nib is plunged inside, right, so the surface is like this. You have a small gap between the back surface of the shoulder and this plate. So when the nib is plunged inside, some metal will try to come out. So a convex surface can give a can accommodate that material. So a convex concave, a concave shoulder will have that advantage, and it will also direct the material to flow, in that a better flow will be there. Well, the tool nib, this is what is called, referred to as the nib, has a diameter about 1/3 of the tool shoulder and typically has a length slightly less than the thickness of the workpiece. That 1/3 of the tool shoulder means nib at the root. The diameter here, the diameter of the nib at the root is generally 1/3. These are all, I mean, there is no hard and fast rule that it has to be so much or that much. What will decide this diameter? If the diameter is too small, it has too less a strength. So, the translational force, it won't be able to withstand, it may break off. If it is too big, too much of translation force is necessary, that also may not be good, right. So, you will have to, these are the aspects which are to be looked into while designing or deciding compound what should be the diameter of this. This 1/3 business is nothing but the ratio of these two diameters, right. If this nib diameter root at the root is more, this has to be more, the entire shoulder diameter will be more. If the nib diameter is less, the shoulder diameter also can be made less. It is generally on the ratio of 1:3, that is what. So, if I am welding, assume I am welding two aluminum plates, suppose for and a certain thickness of aluminum plate, say 10 millimeter thick aluminum plates are being welded. So, for that I need a certain kind of a tool geometry having the this pin diameter of say 8 millimeter. Now, if I want to weld a 20 millimeter thick aluminum plate, maybe this 8 millimeter will be too less, you have to increase that, otherwise it will not have enough strength, it may break off. Or think of it is 10 millimeter aluminum. Now, assume you are welding 10 millimeter steel, it can be different altogether, because in steel you need much higher, the material is much more, I mean stronger, much harder than aluminum, right. And to make it sufficiently softer to apply the solid state welding process, you have to raise the temperature much more. You will have to attain around 800, 900 or probably 1000 degrees centigrade, right. So, there again this diameter will matter, that how much you are putting, right. Anyway, so these are some of the aspects which will decide on the diameter of the tool nib. And another thing is the length, the height of the nib, how much is that? Just less than the thickness of the workpiece. For you can see the configuration how the welding is done. If it is more than the thickness of the workpiece, it will cut through, right. If it is little less, somewhat less than that, then there will be a unfused zone, so called unwelded zone. That means, if the plate thickness is this, and so this is the butt, and the nib is such that it plunges inside up to this much, then what happens? This part remains unwelded, which will be a gross defect, because that unwelded part will act as a essentially a discontinuity in the structure, that will act as a crack equivalent to that of a crack. So, obviously, the structure will fail at that point. So, you will have to have that, how much? Not exactly equal to that of the plate thickness being welded, little less than that. Why? Because under the pressure it will plunge further inside. So, that again brings in another limitation. That means, for every thickness of plate you will have to have a tool. Like a single welding torch can weld plate of 5 millimeter as well as plate of 50 millimeter. It depends on how many run you go on giving, you go on depositing. But here a tool for 10 millimeter will not be suitable for welding a 12 millimeter plate or 8 millimeter plate. You will have to have, for every thickness of plate, you will have to have a tool for that, because of the nib dimension. So, these are some of the types of tools, as you can see. I mean, these nibs, you have all kinds of configurations, right, all kinds of different configurations. So, this is what is the shoulder, right. This part is referred to as the shoulder of the tool, right, and this is the nib which plunges inside. This is another technique within that welding. It's a orbital motion of the tool is given, is achieved by inclining the longitudinal axis of the tool. In these cases, my longitudinal axis is perpendicular to the plate surface. Now, if I incline it a little bit, then what happens? It will give a skewed motion. It will give a skewed motion, elliptical motion will be executed, right. So, that increases the ratio of the swept volume to the physical volume of the tool. When the tool axis is perpendicular to that of the plate, then the amount of metal being swept, being moved from the trailing edge to the, from the forward edge, leading edge to the trailing edge, the metal being stirred, metal being moved is equal to the volume of the tool nib, because that the nib is penetrating in the metal, that much of amount of metal is getting displaced. But if I incline the axis of the same tool, then what will happen? It will move in this fashion, a skewed fashion, right, and execute a motion wherein the swept volume will be more than the physical volume of the tool, right. So, that is what is being said, that it increases the ratio of the swept volume to the physical volume of the tool, which is referred to as the dynamic to static volume ratio. Static volume is the volume of the tool, of the nib, of the probe. It is referred to as nib, it is referred to as probe, right, that small part. And in dynamic state, it is sweeping a bigger volume. So, this parameter has a significant effect towards achieving required level of both weld quality as well as process efficiency, this ratio. Anyway, there are not much we have said that how it will affect if the volume is more or less, but this is another technique which also can have a significant effect on the process efficiency. Well, let us go to the tool shoulder material and the backing material. As I already mentioned, the tool shoulder material plays an important role in the heat generation process, because here you see in the friction stir welding, we said that the primary parameters are nothing but your primary parameters are, well, RPM, downward force, right, and what is that, and the weld speed, we can say. Instead of this will correlate to transverse force, or translational force, that means to move, make it move. But controllable parameters are this: increasing weld speed, decreasing weld speed, well, this force may be more or less, etc., right. But essentially these two are responsible for the heat generation. More the RPM, more is the heat, right. More the force, more is the frictional for a given material, more is the frictional force. So, more is the heat. So, the total heat generation depends on the downward force and the RPM. They are the two basic parameters. So, downward force and RPM gives the controls the heat generation, primary thing. And then comes how much heat is utilized. That means what is the heat loss. So, heat loss, if we talk about, one of the most important is the tool material, because you see the whatever heat is generated, that is generated locally. Like in case of fusion welding, because of the arc heat, the immediate metal gets melted and that heat gets conducted and thereby further metal is melted and other aspects of deformation of stresses are formed. Here, because of the local friction, locally heat is generated and the heat gets conducted to further plastify the material, right. So, the entire heat is contained in the location where the nib is, where the tool is, right. So, here the case of heat loss, like in case of electric arc welding, say gas metal arc welding, we said thermal efficiency is of the order of 0.6. Why? That what does that mean? That means 40% of the heat generated is wasted. How it is wasted? One of the waste was because of the inert gas shielding is being given, that means you are putting in a jet of inert gas. So, that is taking out the heat by way of convection. Then some part is lost by way of conduction in the plate, some part is lost by way of conduction in the electrode, some part is lost by way of radiation from the surface. Right. Here the primary loss is conduction through the tool material, because there is no inert gas flowing in the thing such that a convection loss would be there. There is not much of radiation loss because the heat generated is much less. Radiation loss, as you know, it is proportional to the T to the power 4, right. And the primary heat what is generated is covered by the shoulder material. So, total heat loss would be by your conduction through the tool material. So, that is how the tool material plays an important role in the process. So, if you use a very conducting material and make a tool out of it, your weld will be I mean, you may not be able to achieve required quality of the weld because much of heat will be lost, right. So, that is how that plays an important role. Compared to tool steel, the shoulder, here some example has been given. The shoulder made from zirconia engineering ceramic seems to generate approximately, you see the difference, 30 to 70% more heat depending on the weld parameters. Weld parameters means nothing but F and RPM, downward force and the RPM, they are the two basic parameters. What is this tool steel? Tool steel is nothing but this type of steel which is I mean from which you generally make those lathe machine, tool bits, drill bits, all that. That means they are of sufficient sufficient strength they have, and also they can withstand sufficient raise in temperature, sufficient level of high temperature, and still maintain the required strength. So, it says that the shoulder portion, if it is made of zirconia, then it can give more heat. What extent? It can be as high as even 70% extra heat. Why? Essentially, this zirconia increases the coefficient of friction, that is number one, and number two, it is a very good insulator. That means heat loss is reduced substantially, provided one can use this, then you have this benefit. Welding efficiency is affected by the heat loss through the tool as well as the backing bar. So, that is also is there, the backing bar. So, as you can see, the heat is generated here. So, heat loss would be through the tool as well as through the backing bar. Also heat loss would be there in the bar, that means the backing bar also will take out heat, right. So, that again tells us what the backing bar material should be, and that means it also ought to be of a material which has a lesser thermal conductivity. Using a tool material having low thermal conductivity along with suitable non-conducting backing bar, heat loss can be substantially reduced. This will, and once this can be reduced, it will enable increasing welding speed, right. Increase in welding speed necessitates a similar increase in rotational speed to get sound welds. So once you can reduce the heat loss by providing suitable material for tool as well as backing bar, you can go for a higher heat generation, means you can increase the weld speed, and once you increase the weld speed, then also it says to have the simultaneously the rotational speed also may need to be increased to get sound welds. So then we come to see how the heat is generated and how it is quantified in this. So heat generated in FSW process increases, right, as we have already said, with increasing tool rotational speed as well as downward force. The simple reason, as the downward force increases, your frictional force increases. Travel rate influences rate of heat input, same as that of fusion welding. With the travel rate, higher the travel speed, higher the welding speed, less is the rate of heat input. And here it affects the material flow around the tool nib, So very high travel speed, you may not be able to have the material stirring action properly. Like in fusion welding, very high travel speed, what happened? Very high travel speed may had led to defects like undercut. That means the metal could not flow or fill up the entire gap, entire root gap, entire joint geometry, such that you achieve a proper top bead profile, top reinforcement. So there is a lack of deposition on the sides of the weld bead or the top reinforcement. If there is a lack of deposition on the side, that leads to undercut. That defect is called undercut. So that would have happened if you have a high welding speed, because before the molten metal could distribute itself evenly, as well as sufficient of base metal has been melted, it moves out. High welding speed means what? You are moving away the heat source, you are not allowing the heat to remain in the place for a longer time, or in other words, heat residence time is reduced. And once the heat residence time is reduced, means what? Faster freezing will take place, metal will solidify very fast. There can be lesser melting of the parent metal will take place, because parent metal is not getting enough heat. So it will lead to defects like undercut, it will lead to defects like porosity, because gas will get entrapped, it cannot come out. It might lead to defects like slag inclusion, because the molten slag may remain entrapped, because it should float up. When the welding is being done, there is a churning action going on in the molten metal. So in the churning action, the metal is moving about, the molten slag is moving about, they are all mixed. So it should have time to float up. Now if I move the heat very fast, it will solidify, right. So all those defects may occur. Similarly here, the travel speed, the rate of, it will affect the rate of heat input. Here it will affect the material flow, because here the physical material flow is taking place from the leading edge to the trailing edge. Around the nib, the metal is getting stirred, right. All the relevant parameters are, for heat generation, there is a time of indentation of the tool, the shoulder radius, how big is the radius, obviously, because the shoulder adds to, it supplements the heat, the friction from the shoulder. The shoulder angle and the FSW tool, of the FSW tool, that angle which we are talking about. Well, the time of indentation of the tool, that indentation means that period between the instant the tool contacts the workpiece and the instant the tool begins moving along the joint. That time is important because when the tool is it's rotating and it touches the surface, it's still rotating and you are applying a downward force, so it will plunge inside and then you will start moving it, right? Then you will start moving it. So, how long you have hold it at that place and then started moving it, that is the indentation time. That time can range from 5 to 30 seconds, because longer it is there, it is generating more and more heat, but after some time it attains a steady state. It does not generate further heat, but the cooling starts, because when it is rotating, it has gone inside, the friction has decreased, because it has initial friction will be very high, but the material has become softer under the heat, friction has decreased. So, there can be a reduction in heat generation. So, the indentation time, if you keep for a very long time and then try to move, it will not move, because the heat, the plate has cooled down, right. Whereas, you plunge it down and immediately try to move, you may break the nib, because the plate ahead has not become soft enough. You have to give some time to heat, also enough heat to get generated and the heat to flow, right. So, that is what is the indentation time, it is around 5 to 30 seconds. So, these are the finer kind of parameters one can say which controls the welding process. We said here we have primarily 3 variables, weld variables, that is your downward force, RPM and the travel speed. Indentation time is one of the finer variable. During this period, generated heat spreads in the vicinity of the tool nib, softening the adjacent material and stabilizing material flow, right, around the tool nib. So, that is how you can see, that is something equivalent to like your plate cutting using oxyacetylene flame. You will have to heat it up to the required temperature where the ignition process starts, the oxidation process, vigorous oxidation process starts, right, and then you keep moving continuously. Here the indentation time is at the initial and then you go on moving it, you will not have to stop anywhere. If the period is too short, defects can appear in the initial part of the weld. The tool shoulder angle allows a gradual decrease, increase of the pressure on the top surface of the plate, right. This is about the shoulder angle. The angle is generally of the order of 3 degrees. The very nominal angle is provided. This geometry what you have already seen. This angle, this alpha, this angle is barely around 2 to 3 degrees. Anyway, these are some of the things. It is essentially, it depends the heat generation, because you see the heat is generated from 3 surfaces. First, it is the bottom surface, this flat part it touches, then this surface of the nib and then the shoulder. And here the shoulder also, you see, once it is concave, this shoulder does not generate any heat, because that is not in contact immediately. Only when some metal is getting expelled, if it is, then there will be some contact. Otherwise, the shoulder at the periphery, which is flat again, which is making contact. So, these are the components of the, so considering the concave shoulder, the heat generated is calculated, it is primarily the omega is the, it's your RPM, the angular velocity, right, on that it depends. And well, these are RS and RP are the physical dimensions. That means this part, the outer radius and the inner radius. This RP is the radius of this, and the nib, and this is the radius to the tool shoulder. So that is how, and then there the heat generated from the nib side, that is say Q2 on the side surface, and then Q3 is the heat generated from the tip flat surface. So one is at the shoulder, the nib flat surface, and the nib side surface. So the total heat is obviously the summation of all these three, and then heat transfer into the tool and workpiece. We have talked about it. Depending on the material thermal conductivity, your heat gets dissipated in the tool. So if there is insufficient heat from the friction, that could lead to breakage of the tool nib. So these are the important aspects. That means it not only you won't be able to weld, but you will damage the tool nib. The tool nib gets damaged, right? So these are also important. Like in fusion welding, if the heat is insufficient, well, you may not have proper deposition, you may not have proper fusion. That means there can be lack of fusion, lack of deposition. But as such, to the welding equipment there is no damage, right? But here the welding equipment, the tool will get damaged. So depending on thermal conductivity of the tool material, 95% is transferred to the workpiece, only 5% to the tool. This is provided the material is highly non-conducting. If you choose a wrong material, if the tool is made up of a material which is, that means this kind of heat distribution, if it is there, that so it is that means the heat loss is much less. Ideally it should have been 0, right, since that is not feasible. So at least 95% should be transferred to the workpiece. Maximum temperature created by friction stir welding process is generally of the order of 80%, 80 to 90% of the melting temperature. Well, little more about the, I mean, what happens in this, like in welding, thermal welding, what we have seen, the fusion welding, we had as far as the microstructural aspects are concerned, what you saw is you have a fusion zone, you have a heat affected zone. This is the fusion zone, and then you have heat affected zone, and this is your parent metal or the base metal. So in the base metal there is no change in microstructure, only in the heat affected zone there will be some change, and fusion zone. Here you have what is called the equivalent of that is TMAZ, thermomechanically affected zone and heat affected zone. This is base metal. Right. You have thermomechanically affected zone. Within that the weld nugget, I mean wherever the welding, the two has got, I mean both the plates have got the so called metal stirring has taken place, and the so called weld deposit has formed, that is the weld nugget, that is within the thermomechanical affected zone. That means this part is thermomechanically affected. In welding it was only fusion and then heat affected. Okay, so little more we will see tomorrow.